The next of the three kinds of t-tests we're going to talk about is an independent samples t-test. And if you will turn to, and we'll use things from both books. If you will turn to chapter 14 in the Whit book, and we're going to be looking at lesson 24, I think, in the 24 in the Green and Salcombe book. So let's look at the hardback book first. Chapter 14, page 285. An independent samples t-test is probably the most common that you're going to have. Because let's say, give myself room to work here. Here's an example of an independent t-test. Oops, not that. There we go. All right. Let's say I've got I've got two classes. I've got class X and I've got class Y. And I've got all oversimplified. I've got some test scores. For class X, I've got a 90, a 92, a 91, a 75, and a 78. For class 2, I've got a 93, an 88, a 95, an 80, and an 85. So I could calculate the average for each of these, right? Okay, what's the average for class 1? I don't know, I just made the numbers up. Somebody jump on your slide rule and tell me real quick. So X bar is going to be something. Then we're going to calculate what we'll call Y bar. I'm sorry, your calculator did not have a Y, so it won't work. Yeah, this is not the hard part of the course. Apparently I'm not, no. Try that again. 85.2 for the X's? Okay. Somebody check it, amen that. Oh, that doesn't mean nothing. So Miss Jones has a test average of 85.2. What's the Y one? Pressure's on. 88.2, somebody says. Two people say that. So, well, I've got a motion and a second. Any objection? So Miss Jones has an average, class average of 85.2, and Miss Smith has a class average of 88.2. So we're obviously going to evaluate Miss Smith higher than Miss Jones, right? Which is kind of the way we do things, but not going to get into all that. But the question, statistically, the question is there a significant difference between the X average and the Y average? Now, what is different about this and the single sample or one sample t-test is I've got two different sets of numbers. So it's no longer a single sample. I've got a bunch of X numbers, I've got a bunch of Y numbers. Now the way I kind of set the scenario, if you're a student in one, you're not a student in the other. So the groups are independent of each other. There's not any overlap. So this would call for an independent t-test. Now I don't know the answer if there's a significant difference between 85 and 88. I don't know. I'm not going to run the numbers to see, but I'm going to come up with some other examples that we will run the numbers and see. But essentially, that's what an independent t-test is. You got a bunch of numbers in this group, and you got a bunch of numbers in that group. and you want to see if there's a significant difference between the average of the two groups. So again, a significant difference in the means. So you'll remember that when we started this in the analysis of SPSS, we went to compare means. So we're still comparing means. Actually, it's even more appropriate now because before we had only one mean. Now we've got two means. So we're going to compare two means. So if you look on chapter 14, they've got a scenario, and again, you've got to skip over about 10 different pages to get the whole picture for what it is. And I've got some, excuse me, we have some athletes, and this is kind of a timely example with all the Lance Armstrong stuff lately. During the recent Tour de France, there you go. I'm on somewhere between 286 and the next 10 pages. I'm going to flip back and forth a lot. The scenario is on page 286. We've got some athletes who use this stuff and some athletes who don't use this stuff. And we want to compare their performance. So if you scroll over pages, and you can just walk with me very quickly over this. I'm not too worried about the wording of the null hypothesis and all this mess. What I do have fun pointing out is on page 291, the formula for the t-value for independent samples. The kind of turquoise box right about halfway down on page 291. I heard the word gross. Okay. I'll buy that. That's fine. I don't like this formula. I don't want to use it. However, if you look at it, though, it's not that messy. You know, you're looking at the difference of means. You're looking at the difference of population means, sample means and population means, and you're looking at the difference in the denominator has to do with standard deviation or standard error. The box on page 293 works this stuff out kind of by hand. Let me just point out a couple things. Look at the t-value. The t-value is 2.16. I'm not going to get it the way they get it. I'm going to get it the lazy way. Notice the t-value is 2.16 on page 293 in the box. Also notice the wording of the research problem, or the question. The question is, does the population mean endurance score for treatment patients exceed that for control patients? If you take the stuff, is the performance higher than the ones who don't take the stuff? So is that one-tailed or two-tailed? That's a one-tailed, so it's a directional test. So we're going to have to remember something in a minute. If you scroll over to the page 294, you get really scared. Because that's where it shows you all the messy stuff. Okay, here's what I'm going to do. It's one-tailed. The question was, how did you know it was one-tailed? Because on page 293, the question is, does the population mean exceed? That means, is it higher than? Not just is it different, but is it higher than? It specifies a direction. Go ahead. Let's open up a blank SPSS document or file. Now, notice the way the data is presented on page 294. We're measuring endurance. That's our measure of performance, endurance. The table under B is where the data would be. We've got EPO and control. Don't worry about the second and the fourth columns because that's squaring what the endurance numbers are. We don't have to do that. That's part of the formula in the t-test, but we're going to have SPSS do it without that. They know the formula. What are our two variables? Let's go to variable view and name our variables. We can name them EPO and control, but I've got to say, let's call that treatment. Okay? I'm going to call it treatment. Now, watch what I'm going to do. I'm going to call it treatment. I'm going to go over here to labels. I'm going to enter either zeros or ones. And I'm going to let 0 be the EPO group. Okay, let me do that again. Go to Labels and just click in the right part of that little rectangle there, and you'll get a box asking you how you want those labels. Let me show you again. Because, label it why? Because I want to tell me which is which. I don't want to have to remember what 0 is and what 1 is. I'm too lazy. Okay. Point to label. I'm sorry, point to, point to value. Value, I'm sorry. Yeah, it says value labels, but that's past the label. I know, it's past the label column. Okay, so we're going to let 0, so I'm going to let a value of 0 be labeled by EPO. Now, you can choose 1s and 2s if you want to. You can choose anything you want. I'm just going to use 0s and 1 because it's just easier to do that with. Hey, well, okay, tell you, we'll call it 1. How's that? Make you happy? It doesn't matter to answer your question. Yes. Yep. Yep. As long as you keep straight with that, I'm gonna let 1 be EPO. As long as you keep straight what 1 means and what 2 means. So I'm gonna tell it 1 is going to be labeled as EPO. I'm going to add that, and it'll tell me 1 equals EPO. My other label is 2, and you suggested I use the word control. So 2 and control. And I have to add it because it doesn't know you're finished talking to it yet. So you have to click add. It'll say 2 equals control as soon as I do that. There it is. And we're okay with that. So the kind of treatment, whether you get treatment or not, is one of the variables. What's the other variable? What are we measuring? Okay, let's call it let's call it endurance. But that is okay. So the other was we're measuring endurance. So I'm just going to type in endurance. Click off the cell. If we go to data view, we will see these as column headings. Now, here's something that's going to be a little different than the way we're looking at data presented in the book or that I gave you in the testing example a minute ago. I've got X1 columns of 12, 5, 11, 11, 9, and 18 on page 294. And then I've got control numbers as 7, 3, 4, 6, 3, and 13. I'm going to put all those in the same column because they're all measures of endurance. So they all go in this endurance column. I'm going to go ahead and fill this out first. Well, yes, the endurance does have values. The first value is going to be 12. Oh, no, yeah, okay, no, we did not label values for endurance. You're right. Excuse me. So my EPO numbers are 12, 5, 11, 11, 9, and 18. Is that all of them? Is that 6 of them? It is. And the other numbers, again, they're still measures of endurance. I'll tell you, let me do this first. Those measures of endurance are the treatment that got the EPO, the ones. So those are my EPO numbers, and you put ones beside all of them. This particular person had an endurance of 12 got the EPO. This particular person had an endurance of 5 got the EPO. But we also had 6 people who did not get the EPO. Those are 7, 3, 4, 6, 3, and 13. Boy, that last guy's tough. He had a lot of big endurance score without it. Exactly, and those should all be 2s. So, for example, the first person was 7. 7 was in the control group. That's what a 2 meant. So, again, keep in mind that a column represents values of a variable. So all my endurance values are in the same column. keep in mind a column represents values of a variable. I think I remembered it. Everything in a column is a measure of the same variable. Therefore, everything in this column is a measure of endurance. Now, those people with the endurance scores are in two different groups, so I use another column to identify which group they're in. Group 1 or Group 2, and we've already named what those are. Yes, our variable names are column headings. That was true from the first time we ever saw this stuff. It's still true. It's just a little tricky here because a lot of times in an independent t-test, you've got the groups in one group in one column and the other group in the other column. All those values go in the same column. It looks a little counterintuitive until you kind of get used to it. Yes, because I'm labeling what kind of treatment it is. I'm not labeling the endurance. That's just minutes. Okay. And let you mentally catch up again for a second. So we want to see if there's a significant difference, and it's a one-tailed difference. We keep that in mind, between the endurance scores of those who are in the first group compared to the endurance scores of those who are in the second group. So what group is it in, and what's your endurance score? Now, it does not matter which you have in which column. You could have endurance in the first column and treatment in the second column. It doesn't make any difference. Excuse me. Okay, so we're going to, I bet you know what we do next. We're going to go analyze. I bet you know what we do next. We're going to compare means. But we're going to select, comparing means, we're going to do that by using an independent sample t-test. Because again, these are independent groups. If you're in one group, you're not in the other group. The numbers and the members of the groups are independent of each other. Scoring 11, scoring an endurance score of 11 doesn't have anything to do with scoring somebody else scoring a 6. They're totally separate numbers. So when I select and then click this independent sample t-test, again, I'm going to get my window with two big boxes again. Now I've got two things. I've got test variable and grouping variable. Now, if you think about this, this does kind of make sense. Which do you suppose the grouping variable would be? The one that indicates the group. Is it the control group or is it the experimental group? So treatment goes in here. Now, it's going to ask me for something else. I'm going to come back to it in a minute. But as soon as I put treatment there, I'm going to get two question marks. I'll come back to that in a minute. Endurance, those are the values we're testing. This endurance average against that endurance average, grouped by whether they got the treatment or not. Now, those two question marks back here, okay, this is not rocket surgery. Matter of fact, you'd have trouble getting this wrong. I don't even know why it makes you do this, but it does. When I click Define Groups, I'm going to let Group 1 be 1, and I'm going to let Group 2 be 2. Any questions on that? Let me go back and see where you got that again. Okay. When your treatment is highlighted as the grouping variable, it's got two question marks. It wants you to define those. I don't know why it asks you because you've already put the values in there. Why can't it just get them? But it doesn't. Anyway. So click Define Groups, and we're going to call Group 1, 1, and we're going to call Group 2, 2. Didn't mix that up for anybody, did I? Group 1 is 1, Group 2 is 2. It is if you use 1s and 2s. And I'm glad you caught me. I should not. If I'd used the 0s and 1s, I'd have had to use those. But I'm glad I caught myself and didn't do that. So yeah, for an independent t-test, use 1s and 2s. Just kind of standard. That way, that will always be the same as this. So I'm going to click Continue. And my options, what did it say about the alpha level or the level of significance? I'm sure I read that somewhere. I don't remember what it is. Oh, so yeah, okay. It asks for the .05 level, so I like my 95% confidence interval. So I'm good with that. So we're ready to click OK and get an output window. Now remember that the t-value is 2.16. So click OK. There's my output window. I'm going to move things over a little bit. It's hard getting this on the whole screen, but I think we're kind of okay. All right, for right now, let me tell you what to look at and what to ignore. Let's look at the second part of the table. You see where it says equal variance is assumed and not assumed? We're going to ignore that bottom line for right now. I'll come back and talk about that a little later. Just don't even worry about that. So I've got, and don't worry about this either. The part I X'd out tells you if you should use the top or bottom. The vast majority of the time you get the same results anyway, so let's not belabor the details right now. But look at my t-value. Hey, what did we say t was a minute ago? I said remember. What was the t-value? It gives it to you as calculated on page 295. Yeah, t was 2.16. We get 2.152. The difference is there's a little round-off error here. And I think you may have a homework quiz where there's going to be a lot of round-off error. I've got to go back and catch that again. But so I'm going to get a little bit of difference. I'm going to get pretty close, though. And actually, this 2.152 is probably a better number, probably more accurate one, because when you crank this stuff out by hand, you end up rounding to like a couple decimal places every step, and the computer can take into account more than that. So there's my t-value. Here is my, I really would like to get more on the screen here. Okay. Perfect. Perfect enough. All right. Don't worry about that. All right. Hey, look at those labels there. The EPO had a mean of 11. The control had a mean of 6. The question is 11 significantly higher than 6? So what's the difference between 11 and 6? Not a trick question either. The difference between 11 and 6 is 5. That's the mean difference, 5. So somewhere, again, don't worry about this, somewhere we're going to write the t-value, the degrees of freedom, the p-value, and we're not going to write it now, but there's our level of significance. So somewhere we're going to write t for 10 degrees of freedom. How do you suppose we get 10 degrees of freedom out of this when I have two different samples? Now I've got 12 in all, correct. I've got to take one off for each group, exactly. So my degrees of freedom for an independent samples t-test is calculated by the first n plus the second n minus 2. It's minus 1 for each of them. Or you can look at it like this. The first group has an n of 6. There's 5 degrees of freedom. The second group has an n of 6. There's another 5 degrees of freedom. That's so we get 10 altogether. So t for 10 degrees of freedom, that value is 2.152. My p-value is, now this is a one-directional, one-tail t-test. Because see, this is a significance for two tails. So what's the one tail? What do you do to the p-value? What do you do to a two-tail p-value to get a one-tailed p-value? Divide it in 2 because you're putting things together. So 0.057 divided by 2 is 0.0285. So we'll call that p is equal to 0.02. We'll round down on. Actually, we'll round up on this. I'll call that 0.295. 0.029, I mean. Now this is very important because is there a significant difference now? Is the EPO significantly higher than the control? And the answer is yes, because that's less than 0.05. But see, if I was running it as a two-tail test, it wouldn't be. Yes. What comment was, because the one-tail test, does it matter zeros in the confidence interval? No, because everything, it's giving you two-tailed information here. Everything doesn't transfer over to change it to one-tail, just the p-value. Yes. The information we're seeing here is two-tailed. But we had to turn it into two-tailed. The only thing I'm going to worry about turning into two-tailed is just the p-value right here. So, if you look at the way they concluded this problem, and I'll see where it... Look back on page 293, which is like 2 pages before they work it out. See what I mean? We reject the null hypothesis because, and again, they're comparing the number, the t-value to a table. We don't do that anymore. We just read the p-value. So look at the interpretation. The last line of it. There is evidence, and I don't like the way they say this. I don't like they say that EPO increases. Okay, there's evidence because it is an increase, but we don't know that EPO is the reason for that. Maybe we just happen to, with a random sample of 6, maybe you just picked out 6 of the high one, 6 of the low one, and the other one. I would say there's evidence that the EPO endurance scales exceed the control endurance scales. I would say it that way. EPO endurance scales are significantly greater than control endurance scores. EPO endurance scores are significantly greater than control endurance scores. I meant scores. I think I said scores the second time. Should be scores. Well, no, nothing's always. Probably, I don't know. The question was it always or probably not. I don't know. It is here. Let me try saying it one more time correctly this time. EPO endurance scores are significantly greater than control endurance scores. Yes. Well, we would say we're going to reject the null. And then somewhere, you'll see as we go over the write-up and a couple more examples and another kind of t-test, you'll see when we write up the example, toward the end of that write-up somewhere, you're going to say something like this in plain English. Just like we did with the correlation. You end up saying something in plain English. After you go through all the rigmarole of all the, nulls and alpha p-values and all that stuff, you say, okay, it's a significantly positive strong positive correlation. Or in this case, like I say, the EPO endurance scores are significantly greater than controlled endurance scores. Okay. Okay. Greater than what? The comment was, no, okay, well, you can't say that because they're on, no, you can't say that either because they're on different scales. I'm pretty sure you're at, the comment was made, the write-up was done on the data analysis scores, and the question was, can you say feeling scores are higher or lower or different than attitudes? You can't because feelings were 1 to 5, attitudes were, what, 10 to 15 or whatever. So attitude scores are going to be higher. Now, the question was, do they correlate? They don't have to be on in the same scale to get a correlation. Do the high scores go with do the high scores in one go with the high scores in the other? You're not asking for a difference. There's got to be a difference. I mean, there's going to be. Here's a good example. Hey, is there a difference in ACT and SAT scores? Yes. SAT is going to be higher because it's on a different scale. That's not a helpful statement to make. Now, is there a significant correlation? Ah, that's more interesting. Yeah, that correlation, it works for a correlation. It doesn't work to compare the actual scores. It works to correlate the scores. But it doesn't work to compare them in terms of which is higher or lower. Yeah, because they're just two different. It's apples and oranges. Okay. Okay, any other questions about this? Otherwise, I want to do another example from Green Falcon, where we already have the data. So if you'll turn to Lesson 24, and you'll call up Lesson 24 Data File 1. Why am I writing on that? You can get rid of this one. Well, yeah, don't save everything, because if you save everything, you won't know what junk to wade through later. Now, you may want to, well, when you write up a t-test, you're going to have your choice of which exercise we've done. You're going to have a bunch of examples to choose from. Lesson 24, Data File 1. It looks like this. You got stress in one column and talk in the other column. And if you'll look while you're calling that up, or when you get a chance, if you'll look at the scenario on page 175, where Bart is interested in determining if individuals talk more when they're nervous. And you don't have to read the scenario, but read the key research question on the bottom, page 177, where it says, does the average amount of talking differ under low stress versus high stress conditions? As they phrase it there, it's a two-tell t-test. It's the first line of the scenario, so it kind of sounds like one tell, but we'll go with the way they word the question. Okay. You've already got the data entered. So if we look at variable view, we're going to see, and I think they've already got this labeled too. Notice the values. It says 1 is low stress and 2 is high stress. So if I look at the data, I've got all these ones are low stress conditions, and what he does, he creates or somehow differentiates between what's low stress and what's high stress. If you look at the table 17, it's top page 178, the stress is the grouping or independent variable. Independent variables and grouping variables tend to be synonymous. The stress value distinguishes two treatment conditions. 1 is low stress, 2 is high stress. And the talk value, or the talk variable, is the dependent variable. That's the percent of time each student talked during a 10-minute test period. Just a higher number means more talk. That's all we need to know about it. So I've got my low stress talkers, cases 1 to 15. I've got my high stress talkers, cases 16 through 30. Now let me point out something here that's not evident. The groups do not have to be the same size, which is really good because it would be really messy if they did. Now you could have 25 in one and 30 in another. It's okay. The groups do not have to be the same size. And we'll see some examples that they just don't give us one right here. So I've got my low stress talkers, I've got my high stress talkers. I want to know if there's a difference. If one is more or less than the other. So we're going to go to Analyze, where we're going next. Compare means, where we're going next. The question was, I've got a question I've got partially covered up. Lesson 20, which part of lesson 24? Lesson 24, data file 1. Lesson 24, data file 1. That should be your greetings. It's on. I post these data on D2L, and again, it's strongly suggest you put them on the flash drive or your hard drive or something. Otherwise, it's easier to load them from there than it is off D2L. Okay, so you said to go to Analyze, Compare means. Yeah, okay, there you go. Yeah, you can see the column, the page heading. It's an independent sample t-test because you're either in the low stress or the high stress group. No overlap, no, just one or the other. I'm going to click Independent Samples T-Test, and my window with 2 boxes is going to come up again. And I've got 2 variables in the left box and a couple of boxes of different sizes in the right hand. What goes where? Stress is grouping, correct. Percent time is test. Percent time talking. Now notice the 2 question marks here, and by the way, if you don't click on that box where you put stress, it won't let you do anything with it. You got to click on this first because it wants to know that's the one you're talking about. So I'm going to define groups, and again we've done this easily. Group 1 is 1. Group 2 is 2. Does it say anything about the level of significance? Could be anywhere. Or it could be nowhere. The question is, where do we find it? I don't see it anywhere, which answers our question. If we don't see it, we're looking at the 0.05 level of significance, which means we want the 95% confidence interval. So we're okay with that. So I'm going to continue, and all of a sudden, once I click continue, I've got my 1s and 2 in my after the stress in parentheses there, which is what I want. I click OK. I'm going to get an output window. See if I can look at everything together here. That's pretty good. Okay. Again, we are going to ignore the very bottom line and that. And sure enough, I've got low and high stress labeled. There's 15 in each group. There doesn't have to be. The low stress talked at 45. The high stress talked at 22. And my key numbers here are the t-value, the degrees of freedom. The real key number is the significance. So somewhere we're going to write T for 28 degrees of freedom. Where does 28 come from now? Yes, degrees of freedom. How do we get 28 out of it if it didn't tell us so? Okay, because the number altogether minus 2, minus 1 for each group is 28. Or you've got 14 degrees of freedom in each of 2 groups. So there's my degrees of freedom. The t-value is 2.43. P is equal to 0.022, and that's a significant difference, meaning that there is a significant difference between 45 and 22. Yeah, it looks like those low-stress people talk a lot more. I would have kind of thought the opposite. I guess if people are stressed, they quieten down or something. I don't know, but I guess you can see it either way. So, the plain old English stuff is, yeah, the Low stress people talk significantly more than the high stress people do. Say it again. Yeah, I don't think it does matter. Yep. With these data. Yes, that's a good point. Let me paraphrase what you said. They're not the same people in the low stress group and the high stress group. What if it was the same people, though, and you put them in a low stress situation and you put them in a high stress situation? Ah, that's the next kind of t-test, which I'm not quite ready to go to just yet. But good example, whether you meant to or not. How did you know which was the test and which was the grouping? The group, I don't mean to say, I'm not sure how to say this without saying bad. The grouping is the one where it tells you what the groups are. I mean, I don't know how else to say it, really. The grouping is which group you're in. Either the grouping is with the ones and the twos in this kind of test. That's going to always be the case. You're either in group 1 or you're in group 2. The talk numbers, they don't tell you anything about groups. Just because the person in number 1 talks 31% of the time, that doesn't put him in a group 31. He's in the first group. There's not a group 5 for the second person. That person who talks 5% of the time is in the first group also. I'd like for you, let's take a few minutes and do something. Turn over to page 181 and look at the first exercise. So I want you to call up lesson 24, exercise file 1. And I'm just going to leave this alone for a few minutes. And if you're watching this in the recording later, you can stop the recording if you're not through by the time I get back to it, or pause it. Read the scenario, top page 181 through the first paragraph. This is called the Big Mac problem, or the Big Mac question. The question is, we want to test the hypothesis, and this is not a question, it's a statement, it's a hypothesis, that overweight people, this is a politically incorrect question. Anyway, we think that maybe overweight people eat faster than normal weight people. So we're going to test this hypothesis. We're going to have two people watch people eat at McDonald's. And we're going to see if they order the Big Mac. The Big Mackers, as they are affectionately called by the assistants, are classified as either overweight or normal weight. If the ones are normal, so we identified, here's a good example, we identified 10 overweight, 30 normal weight people. See, the groups are not the same size. That's okay. And the time is how fast they ate their meal. So a shorter time is eating faster. So take just a couple of minutes and analyze this and see what the data says in terms of, do overweight people eat faster than normal weight people? Number 1 is overweight. Number 2 is normal weight. Of course, it'll tell you that. It's already got that programmed in for you. So take just a couple of minutes and go through the procedures, and let's see if you can come out with what I'm going to come up with in a minute, I hope. The question was what's the, well, I'd rather call it the alpha level. Not seen anywhere, we're going to go with a 0.05. Boy, I'm not going to comment on that one. Question is it one tail? I would argue if the way they asked the question, it is one tail. Because the question was, does this group eat faster than the other group? Yeah, faster is one well, not one tail, not just different, but faster. Which way is different? That's direction. Question was on the t-value to use the minus. In this case, I would not use the minus. The only time I would argue using the minus is if it's a one-tail test, which this is, but I would argue that lower tail significant would be. Actually, in this case, though, you're talking about less is faster. Still wouldn't use it. Generally, we don't. Yeah, there's some examples where I would say include the negative, but I just because I'm reluctant to say never do something or always do something. Don't worry about the confidence interval for a one-tail test. Just worry about the p-value and the means. How are we doing at home? Back to your question, I just uncovered, Gail. Yes, that's exactly what it's a way of sorting it. Yes. The question was on rounding. What are you asking about rounding? What is it? But I mean, no. What does the number represent? Okay, the question was, yeah, if it's a t-value, round to two places. If it's a p-value, go out 3. If it's a t-value, you can round to 2 places. If it's a p-value, you can go out to 3. Excuse me. I'm going to go ahead and run through the example real quick. Again, if you're watching the recording of this, if you're not finished, just click pause so you get to where you're caught up, and then you can see if we've done the same thing. Okay, so we're going to compare means. It's an independent samples t-test. Our weight classification is the grouping variable. Our time is the test value. The weights are 1 and 2. I'm just very quickly, again, you can pause if you need to. The defining of the groups are 1 and 2. Oh, you don't know if you're right yet. You could both be wrong. We like the 95% confidence interval, so we're going to leave that alone. Output window. If I could move this over, it would be really good, wouldn't it? There we go. Well, the comment was, it's significant, but I don't know if what answers the question. Well, look at our means. Our overweight mean is 589. Our normal weight mean is 698. Now, since this is time, the lower time means eating faster. That's, I think, what your question was. So, again, we're going to pay attention to the right parts. So, T for 38 degrees of freedom, again, there's 40 altogether, minus 2 groups is 38, or n minus 1 for each of them is still going to give us 38. So T for 38 degrees of freedom. The T value is 3.975. You can round that to 980 if you want to. I'm going to leave the negative off. P is, again, this is a 2-tail P, but if we divide it by 2, we're still going to get 0, but I can't say P is 0. So the P value is less than 0.001. That means, yes, the 589 time is indeed significantly different, or faster in this case, than the 698 time. Again, there's still a lot more politically incorrect examples in these textbooks. This is just the first of several. You'll see others as we go along. Okay, questions, thoughts, comments about that? Did we get the same numbers on that? Okay. Again, this is recorded, so if you need to go back and look at that again. I'm going to do one more example for you just because it brings something up to do that I've shown you one more time. I just don't want to forget about it. Walk with me through the other example, exercise 2. Again, still less than 24, but exercise 2. And that is on the bottom of the page we were just reading a minute ago, the bottom of page 181, where it starts with the paragraph for the data for exercises 6 through 10. Now, I want to know whether there's some kind of difference in terms of whether, it's funny, one of my thesis dissertations was about this. One of my dissertation defenses was about this. Sort of, not this. Just a little more complicated than this, but okay. We've got students, and they're either integrated or they're not integrated. And I've got pre- and post-tests. Now, this is not exactly an independent t-test as we have it set up. I could do a t-test to compare integrated pre-tests with non-integrated pre-tests, or integrated post-tests with non-integrated post-tests, but how do I put pre- and post-tests together? Can I come up with some number from the pre- and post-test that will give us a single score? I could do an average. What they suggest I do, they suggest I do what we refer to as a gain score. Now let me make a disclaimer on gain scores. This is not always the best way to handle differences. Now, it may be that my pretest average for the integrated folks is significantly different at the beginning than the pretest average for the non-integrated folks. But I'm going to calculate a gain score. The problem is that the problem with gain scores is that there's a really big issue if you have either initially high or initially low scores. Because if you've got a bunch of really, really low pretest scores, they're probably going to go up, no matter what you do. If you got a bunch of really, really, really high pretest scores, they may as well go down because that's about the only direction they can go. So gain scores is not really a good statistically thing to do. We've got some adjustment for initial differences that you'll see of 70 and 11 next term. But for right now, we're going to calculate gain scores. So do I have to create another variable here and just say, okay, 96 minus 86 is 10, 85 minus 99 is negative 14? And the answer is yes, I have to do that, but it'll do it for me. So we're going to go to transform. I think it's transform. Yes, transform. And again, you've seen me do this before, but let me just not let this get too far out of mind. I'm going to compute variable. And I'm going to name my new variable here. I'm just going to say gain. How much they gained. And I calculate gain by taking the post test, and you can double click, or you can click on it and use the arrow. The post test minus, I'm going to click minus on my calculator, the pretest. Post test minus, again, with my disclaimer about gain scores not always being a great idea. Sometimes they work okay, but there are a lot of cases where they don't work so well. Yep. Either, yeah, click and use the arrow, or you can double click it, it'll move them over there. So when I click OK, I'm going to see a new column called gain, because that's what I call it. You can call it gain scores if you want. It doesn't matter as long as you know what it is. So when I click OK, as soon as I click OK, no, it doesn't output win anytime you do anything. Wow. Yeah, I just closed. Why am I not getting my OK? I'm stuck. See, it's... Oh, great. It's not doing anything for me. Let me reset, cancel, or anything. Okay. We'll do it this way. Still not. Let's call it up again. Pardon me, sometimes things happen, as you well know. SPSS is not responding. Well, we knew that. Okay, so let's open it again. Give me a second to find it. Okay, here we go. Try again. Yeah, I'm going to close the output window because, like I said, anytime it does anything, it tells you, hey, I did something. Hey, open the file. Hey, you opened the file. Well, I know that. Oh, okay, well, now it did what I asked it. Look, I've got my column of post test scores here. No, it didn't do it. So transform, compute variable, gain, equals post test minus pretest. Let's try again. Output window saying it did something. Yes, I know, I told it to. Now, I've got a column of gain scores. The first gain score is 10 because 96 minus 86 is 10. So what I'm going to do is I'm going to compare the gain scores of the integrated students with the gain scores of the non-integrated students. That's an independent samples t-test. So we're going to go to compare means, independent samples t-test. Now what do I want over here? I've got more options now. The classroom integration is going to be the grouping variable. Okay, we'll go ahead and do that if you like. What goes in test variable? Test variable. It's just the gain, because that's why we calculated that. My defining groups. Again, not rocket surgery. Group 1 is group 1. Group 2 is group 2. So we're ready to continue. And I don't think it says anything else other than in terms of an alpha level or level of significance. So we're going to go with the 0.05, which is our default confidence interval here anyway. Okay, gets us an output window. And it tells us yes, it is. Okay. Let's eliminate what we don't want to do. All right. Look at our means. The integrated had a mean of 9.6. The non-integrated had a mean of 1.5. Again, those are gain scores. So on average, students in the integrated class gain 9.6 points. On average, students in the non-integrated class gain 1.5 points. Well, is that a big deal or not? And we've got enough information here to find out. It's 2-tailed because I just want to see if they're different. Okay, T for 38 degrees of freedom. Again, notice there's 15 in one group and 25 in another group. They don't have to be the same size. Another good example there. T value is 1.778. Got to leave the negative off. P is equal to 0.083. So that 9.6 compared to 1.5 look pretty good, is it? It's actually not. It's not significant because my p-value is not less than 0.05. So there's not a significant difference here. Yeah, it probably is, but not probably enough. There's what a 91.7% chance it is, but I got to have over 95%. I can't have more than a 5% chance of being wrong by saying that. And I do not reject the null. You can say either retain the null or don't reject the null. In plain English, there's not a significant difference between the gain scores of integrated students and the gain scores of non-integrated students. Okay, let me see if I can got the questions from the home crowd, from our homeschoolers. Questions, do we not have to have the p-value? No, because we were doing a two-tail test. We're just saying, is there a difference? I don't think it asked us, yeah, it says hurt or help. That means either way. So it's two-tail, so we don't have to have the p-value. That was a question. Good question. Any other questions? Okay.